Greetings to dear students. In the last video, we have seen the definition of residue of a function at the point. So, residue of a function at the point z equal to a is nothing but the coefficient of 1 by z minus a in the Lorentz series expansion, or the value of 1 by 2 pi I integral over c f of z dz. Okay. So, first example. And f of z is equal to e power z by z square. Okay. So f of z is equal to e power z by z square. So here we have to find the singular point. Okay. So what is the singular point here? 0 is the singular point. Okay. Yeah. So suppose here 0 is a singular point of order what? 2. 0 is a singular point of order 2 because yeah, z minus 0 the whole square. Okay, z minus 0 the whole square. So which can be written as z minus 0 into z minus z minus 0. So 0 is a singular point, and moreover isolated singular points because this function has only one singular point. It's a singular point of order 2. Okay, so here I have written 0 is a pole of f of z of order 2. I will explain later. Okay, so which is equal to 1 by z square. Then we write the expansion of e power z. So 1 by z square into 1 plus expansion of e power z is 1 plus z by 1 factorial plus z square by 2 factorial and so on. Then multiply by 1 by z square, we get 1 by z square plus 1 by z plus 1 by 2 factorial and so on. So the residue of the point, a function f of z at the point 0 is equal to, by the definition, coefficient of 1 by z minus 0. So what is the coefficient of 1 by z minus 0 is nothing but 1. So therefore, the residue of this value is equal to 1. Okay. So I hope this example is clear to you. Okay. Here I have written pole. So I will explain what is pole here. Okay. So let A be an isolated singular point. Okay, isolated singular point. A is an isolated singular point. Okay, then it has three types. It has three types. So first one is removable singularity. First one is removable singularity. The second one is pole, and the third one is essential singularity. So the first one is removable singularity, second one is pole, and the third one is essential singularity. Okay. So removable singularity means when we expand the function f of z, it does not have the terms 1 by z minus a in the denominator part. That is, the function should not contain the value z minus a in the denominator part. Okay, so pole is in the a point is said to be pole and actual singularity is said to be a pole if the function f of z has only finite number of the terms z minus a can occur only at the finite number of terms in the denominator part. If the term z minus a occurs infinite number of terms, then the point a is said to be essential singularity. Okay, so removable singularity means the term z minus a does not occur in the expansion of f of z. Okay, a point in a is said to be pole. When we expand the function f of z, the term z minus a occurs only at finite number of terms in the denominator part. Okay, essential singularity means the term z minus a occur infinite number of terms times in the denominator part. Okay, that is, for example, removable singularity means f of z is equal to. Okay, for example, you can take e power z. Yeah. Okay. So e power z is equal to 1 plus z by 1 factorial plus z square by 2 factorial and so on. Okay, so which means the denominator part does not contain any terms in the form z minus something. Okay, so this is the example of removable singularity. Essential singularity, in the place of z, if you replace z by 1 by z, what do you get? 1 by z here, 1 by z square. So which is equal to 1 plus z into 1 factorial plus 1 by z square into 2 factorial and so on. Okay, so in the denominator part, the term z minus 0 occurs infinite number of times. So therefore, this is an example of essential singularity. Pole means, suppose f of z is equal to 1 by z plus 1 by z plus 1. Okay, then it means the term z minus 0 and z plus 1, the terms of the form z minus a occurs only at the finite number of times. Here, 2 times only it occurs. So therefore, it's an example of pole. Okay, so I hope the definition of removable singularity, pole, and essential singularity is clear to you. Okay, so since e power z by z square, okay, this is occurs only, and I mean, how to say, yeah, e power z by z minus 0 the whole square. The denominator part has only one singular point, and which is pole of order 2. Okay, so next, uh, we have 4 lemmas for to find the residue of the function at the point. Okay, if the point a is a simple pole, then we have 3 formulas. If the point a is a pole of order greater than 1, simple pole means of order 1. For a simple pole, we have 3 formulas, and pole of order greater than 1, we have 1 formula. So with the help of these 4 formulas, we can easily find out the residue of the function at the point. Okay, so first lemma is, if z equal to a is a simple pole for f of z. Okay, if z equal to a is a simple pole for f of z, then residue of f of z at the point a is equal to limit z tends to a, z minus a into f of z. Limit z tends to a, z minus a into f of z. Okay, so for now, we have only know the definition of residue. Okay, so with the help of the definition, we are proving that residue of the function f of z at the point a is equal to limit z tends to a, z minus a into f of z. Okay, so consider the Lorentz series expansion for the function f of z about the point a. Okay, about the point a. Therefore, f of z is equal to summation bn by z minus a the whole power n plus summation an into z minus a the whole power n. If about the point z naught means, in the place of a, you have to write z naught. Okay, so about the point means about the point a means the function should be of the form z minus a. About the origin means we can simply write it as z bn by z power n. If they particularly given a point means you have to expand the function f of z with respect to that point. Okay, so this is the Lorentz series expansion for the function f of z, and also given that z equal to a is a simple pole for f of z. So by the definition of residue, okay, so by the definition of residue of f of z. Look at this one. Residue of f of z at the point a is equal to coefficient of 1 by z minus a in the Lorentz series expansion. Okay, in the Lorentz series expansion, what is the coefficient of 1 by z minus a? Of course, it is b1. When n equal to 1, and the term will become b1 by z minus a. So therefore, the coefficient of 1 by z minus a is b1. Okay, so therefore residue of f of z at the point is a is equal to b1. So mark it as equation 2. So now we have to show that this B1, okay, this B1 equals to, this B1 is equal to limit Z tends to A, Z minus A into F of Z. Okay, we are going to show that this B1 is equal to limit Z tends to A, Z minus A into F of Z. If it is, if they are equal means, then instead of B1, we can write it as residue of F of Z at A. Okay, so our aim is to show that the limit Z tends to A, Z minus A into F of Z is equal to B1. Okay. So for that, first consider Z minus A into F of Z. Already we have F of Z. Now we are multiplying F of Z by Z minus A. So therefore, Z minus A into F of Z is equal to Z minus A into the F of Z terms. B1 by Z minus A plus A naught plus A1 into Z minus A. You note that in the Lorentz series expansion, we have only taken this only, because given that A is a simple pole only. It can, simple pole means it's an order 1, that is Z minus, if F of Z is equal to 1 by Z minus A the whole power R, then A is a pole of order R. Simple pole means is a pole of order 1. Okay, so we have B1 by Z minus A, B2 by Z minus A the whole square cannot occur because A is a simple pole. So the first term only will come, the remaining terms cannot be. Okay, so F of Z is equal to this and Z minus A into F of Z is equal to this. When we multiply F of Z by Z minus A, we get that thing as B1. Z minus A will get cancelled. Second term, Z minus A will come. The third term, Z minus A becomes Z minus A the whole square, and so on. Now I am taking limit Z tends to A. When we take limit Z tends to A, this will becomes what? When limit Z tends to A, this will become A minus A 0. So the remaining terms all will become 0 except the first one. Okay, because it does not have the term Z minus A. So therefore, limit Z tends to A, Z minus A into F of Z is equal to B1. But B1 is nothing but B1 is nothing but what? Residue of F of Z at the point A. Residue of F of Z at the point A. So by substituting the value of B1 here, we get residue of F of Z at the point A is equal to limit Z tends to A, Z minus A into F of Z. So simple formula, if A is the simple pole, then residue of the function F of Z at the point A is equal to limit Z tends to A, Z minus A into F of Z. Okay, so we will see the remaining two definitions in the coming videos. If you have any doubt, then you can put your comments, put your questions in the comment section, or you can ask in the class. Okay, so thank you, dear students. Thank you.